Here at Ultimate Reloader, we like to put things to the test in the lab. In this video, we're going to push Alpha Munitions 7-SWC brass to the absolute limit and capture actual pressure with a new methodology. Check this out. Hey guys, Gavin Gear here from UltimateReloader.com. I'm back with John Miller from DEWEsoft. Thank you very much, John, for joining me.
Thanks for having me.
John is a nerd out data kind of guy. He's an engineer and he works at DEWEsoft. DEWEsoft makes hardware and software solutions for data acquisition. And we've put your equipment through its paces with, let me think, recoil, sound, and pressure. Last time we did pressure, we drilled a hole through the barrel.
Yep.
And it's worked phenomenal. And what I love most about the entire DEWEsoft system is the ease of use of the software. When we can see the data in real time, I mean, we used to scrape through Excel, we used to download CSV files and do a bunch of post-processing just to get some raw numbers. So first off, thank you for partnering with me in some of this research. Let me set the stage and you can sort of talk about this setup that we've got here that's gonna really take things to the next level. So you're gonna wanna check out my video building this rifle. This is a bat hammerhead with a custom rifle barrels blank. It's chambered in 7-SWC. 7-SWC is kind of like most of the power of a 280 AI, but crammed down into a short action. Guys are using it for hunting. Guys are using it for PRS, specifically when you want to buck the wind a little bit better and split the difference. And of course, like anything, there's trade-offs. But what was amazing about this build was how well it shot. Let me show you that real quick. Okay, so this thing is an absolute tack driver. Now I was talking with the guys at Alpha Munitions about this OCD brass, optimized case head design, right? This is where we can go to really, really high pressures without compromising our primer pockets. We've seen it in 308 to 300 Win Mag, our first test, where we basically estimated pressures with quick load. Sure. We saw it with our second test where we pushed 6 GT to beyond 6 Creedmoor velocities. That was with a drilled hole through the barrel right ahead of where the case mouth is to grab that pressure after the bullet goes by. And that's the downside. We had to wait until the bullet goes by, so we missed a little bit of the peak pressure and had to kind of reverse engineer it a little bit, do some back math. This time we've got, I'm excited about this. This is a way to get really accurate pressures, but in a non-destructive manner. Why don't you talk about this setup?
Yeah, so the other methods you were kind of mentioning usually use a piezoelectric element. They can be charge amp or IEPE sensors, and you're exactly right. You have to drill a little hole and then you're directly measuring pressure into a crystal. Here we have a couple of strain gauges, and the only destructive part is you just have to get down to the raw material. So take a coating off or whatnot and then bond that strain gauge to the surface. We've got a couple of rosettes, so we can directly measure those principal strains. And ultimately what we're doing is measuring the pressure inside the vessel. And then what we've done is we've taken that and we've calibrated that in a hydraulic system. So we've taken 1,000 PSI increments all the way to 8,000. In a perfect world, we would have done that to 80,000. But most factory hydraulic systems go up to 10,000, so that was the limitation there. So now we can extrapolate the measured pressure in the barrel, and we can see that in the chamber pressure and the port pressure, if you will, but it's not ported.
Right, and so going back to the calibration process, the reason that I wanted to pressurize the barrel was, I've heard people basically calculate and infer what the strain should be given cross-sectional area and so on and so forth. But there's some things about rifle barrels, like the rifling itself. You've got 4 thou lands on either side, and the lands and the grooves are in a spiral pattern. If we can basically measure a known pressure and a known strain is a percentage elongation, things elongating a little bit, that allows us to get that accurate pressure reading. And again, we don't have to drill any holes here. This is a standard rifle barrel. We didn't have to use a test barrel with the universal receiver, all that. Okay, so that is a little bit of the background. And John brought a DAC module from DEWEsoft that is optimized for use with strain gauges, and we've got 2 of them. We've got one right at the shoulder junction, and then we've got another one that's 1.5 inches ahead of where the case mouth stops. So what'll be interesting, we've calibrated both, is to see what kind of pressures they will evaluate to in real time.
And it's actually 6 strain gauges on 2 rosettes.
True.
That we can get the
Yes.
principal strains to get the best output.
Yes. So what we decided to do is we went kind of way below my load last time. We wanted to show the pressure kind of building incrementally. And so we went in 1 grain increments from 35 all the way up to 44. Remember, we were just shy of 40, and I think we went maybe up to 41 last time. So here's 10 rounds. We'll see how the pressure is building. We'll stop if we need to, if we see pressure signs. But we might come down and load some more ammo and keep going until we see really flattened primers, we see some swipe on the case head, and that kind of thing. So I'm thinking we move the rifle and all the data acquisition gear up to the mid-mountain range, get set up, and let's record some data.
Let's roll.
Awesome.
Starting at 35.
Okay.
Got it.
1923.
Ooh, I got a false trigger from you ejecting that thing.
Oh,
Okay, well, that's fine. Just keep shooting.
okay.
I can just see it in my data.
I'll grab it out. Let's see, this is 36.
Yep. Okay.
2273. Here's 37. Twenty-three 26.1. This is 38. 2374. 39. 2419.3. Ready for 40?
Mm-hmm. Okay. Are we done?
Nope.
41.
2474. 41.
Okay. I'm showing that's at 73.
Okay. 42.
It's getting closer.
2561. Here's 43. 2626.
I saw 82 there. You're still hotter before.
Yeah. Here's 44.
That's the hottest one we've seen so far.
And no pressure signs on this.
That's the hottest one we've measured so far.
Okay.
At 89.
Okay. So that was 44. So I'm wondering what's up with this other ammo then.
So take a look at this real quick. So other than, I should have put a hold off time on one of the triggers, so disregard that line down here.
Okay.
That's nothing.
Yep.
But these are your sequential shots,
Wow.
and then here's your pressures. So we started 35 grains, 56, 57, 60, 63.4, 66.9, 72, 73.6, 79.4, 82.1, 89.5. Going up from 35 to 44.
And no stiff bolt lift on any of those. Usually you're going to get that at 70s. Primers not holding at 80s, right? If you're using an inferior grade brass or whatever.
Right.
So, and that was 2669. So the question is, do we call it good there? Or do we keep going?
I would keep going.
You want to keep going?
Well, I mean, I think 44 is about what we're going to call the max.
Okay.
But until you see, I mean, your gun can handle it.
Yep. Chronograph is ready. Here's 35. $44.
85.
45.
89.6.
Okay, and 46.
93.5. How does that brass look?
We're at 2780. Some swipe from the ejector
Okay.
pocket. I mean, we could keep going. What does it say now? 90 what?
93.5.
93,500? Wow. It's impressive.
Started at 53,000 and worked our way up.
So I think one thing that we can do is we can look at 7 rem mag data for the 180, and we can compare it to this
Sure.
guy here. I wonder where we're at compared to that, you know? This is 28-inch barrel, so we're getting every ever loving bit of velocity out of it, you know? Okay. You like the way it's looking?
Yeah.
Oh,
Looks really
yeah.
good.
Wow. That's awesome. Okay, so we're done with all the shooting. Super, super interesting results. Now,
Yep.
I'll have to say, the first round, we ended up doing 2 rounds. The first round started at 35 and went up to 44. And the curious thing was, we didn't see pressure signs really.
On the brass.
Yeah.
Yeah.
And so the whole point of this video is to see how far we can push things.
Right.
And basically the limiting reactant is pressure signs on the brass, or that stopping point indicator, right? So then the second pass, we went from 35 all the way up to 46. And here's what impressed me. Let's just talk about the velocity data first. So the velocity started at 2196 and it went up to 2782. And so the first thing I did when I got back down to the shop is I opened up the Hornady manual. I looked at the 7 SAUM data. So 7 SAUM, somewhat similar to short action, but it is a Magnum bolt face cartridge. This is a 308 bolt face cartridge.
Right.
We met what 7 SAUM can do, and we were within about 50 feet per second of max load for 7 rem mag.
And that was a smaller bullet.
It was a lighter weight bullet, 5 grains lighter, right? So if you're wondering, if you're gonna look at a 7 SWC and you have alpha brass, you're gonna get some really, really impressive results in terms of velocity. It's gonna be matching a 7 SAUM, and it's gonna come close to and or meet a 7 rem mag for all intents and purposes.
If you really push it.
I'm not saying you should do that, but you know, we were saying for this last round we were going to stop at 45 instead of 46. We're shooting in 100-degree weather. The ammunition was not in the direct sunlight, however, and that would have given us 27.25, right? That is really impressive. So now why don't we talk about the pressure data? This was really, really cool.
Yeah, so what we're looking at right now is it's actually the bore pressure. 35 grains of powder in the cartridge, and we hit about 53.8 KSI, or 53,800 PSI. And we slowly incremented up, and as we hit the 46 grains, we were roughly 93.5. So pretty hot.
Very hot. And the only pressure sign that we saw on the brass for that 46 grain load was a very slight impression of the ejector pocket and a slight amount of swipe around that area. Something that would be, I've seen in multiple SKUs of factory ammunition, and not even shooting in 100-degree weather.
Right.
So the brass, amazing. OCD, totally amazing. Like I said, this is our 3rd experiment with that. So we're at 89,000 PSI at the load that we were gonna stop at. Now, there's also, this is our first time through this whole experiment, and when we calibrated, we saw 2 different things with 2 different regions of that chamber and the bore, respectively. So talk briefly about like what we saw and how we arrived at believing this set of data.
Yeah, okay. Let me jump over, and let's first look at how the 2 pressure readings time align. So basically, if you're following the SAMI standard, you'd use a conformal sensor, and it, the characteristics, the kind of ideal characteristics of the conformal sensor is you have this nice slow buildup, you hit your peak pressure, and then you have a slow build down. With some of the other test methods, like if you're using a case mouth sensor, you kind of miss that nice slow buildup, and then it kind of jumps up. And we really saw that very cleanly in the strain data because, we have one sensor kind of a little bit ahead of where that SAMI location is, right at the shoulder. And then we had a strain gauge slightly in front of that. But we're taking the timeline data very nicely, and the time really lines up nicely. We had a kind of a major discrepancy, and I can show that if I put these on the same scale. So here we can see that the bore was measuring, about 55,000 psi on this shot for that 35 for the 35 grains of powder, and the shoulder was measuring much less, actually kind of unbelievably less. And so we started to really think about the location of that strain gauge, and ultimately, it's not really an isotropic part at that location, and also
In other
you're
words,
having
it's not symmetrical.
it's not symmetrical.
It's not consistent in its geometry.
Yeah, and we in our cal process, it was a static environment, right? So we're basically loading, pressurizing this whole balloon or pressure vessel, and everything is kind of reacting all at those surfaces.
Yep.
In the ballistic event, we're actually starting at the action, and this pressure bulb is moving up, and we kind of think that pressure bulb at that shoulder is giving us kind of some questionable data at the shoulder location. Also, when you're measuring at the conformal sensors and whatnot, the brass has a stiffness as well. So any added strength in the brass would actually usually be assigned as an offset, and this can be a couple thousand psi. I think I've seen it maybe 7,000 psi even. And so that's where that number should come up a little bit. As we look at the bore location, it seems a lot more believable in relation to the velocities that we're seeing, especially when we're seeing some of the effects on the brass at 46 grains of powder.
I'll tell you why I'm going down that line of thought is if we're meeting 7 SOM velocities in a much smaller case, then we're way up there in pressure. And about in this region, right?
Yeah, and really for me, the big takeaway is when I look at the incremental shots, that's incredibly clean, good, believable data. And the relationship from 35 grains to 36 to 37, that all is absolutely believable. I do think we should reevaluate that calibration process.
Yes.
Because I think the industry, in order to believe this type of data, would really like to see maybe a strain gauge at one of those case mouth sensor locations, and how do those correlate. So maybe there's some skew in all of these numbers, but the relative value from one to the other is physics would say spot on.
Right. And every type of measurement, every measurement approach and sensor setup has its pros and its cons, is what I'm learning.
Yeah.
Like the case mouth sensor, we had to pack it with grease, and there's this thing called the pipe effect, and that gives you different resonant type effects, kind of like when you blow into a recorder, these different frequencies and those sorts of things. But yeah, I think if we could do a parallel experiment, 2 different measurement types with 2 different calibration processes, and then compare the results, I think, and then also compute. I don't have a quick load model for this cartridge.
Right, it would be really nice to have.
So that would have made for maybe a more well-rounded experiment, but super exciting to see such clean data, and to see, honestly, just even if we didn't have this DAC system connected, the performance speaks for itself. We saw exceptional accuracy with this particular rifle, very high-end rifle, very stiff barrel, but that's what you do when you want to show absolutely what a cartridge can do, right?
For sure.
And then we saw velocities that are in the Magnum territory, especially short-action Magnum for 7. So, where to go from here? I'd like to, take this offline with you and discuss some different ideas for how we could take it to the next level.
Fine-tune that calibration process. Because, the data looks fantastic.
Right.
It's just getting that, typical hydraulics are made to 10,000 PSI. It's hard to get a system, up. Not a lot of equipment runs at 60,000 PSI.
Yeah.
So that's where that calibration is a little bit more challenging.
Yeah, so we'll see where this goes, but I want to thank you very much.
Thanks for
coming out and lending your expertise and bringing this system that works with the strain gauges and that kind of thing. Here's what we'd like to know from you is, first, what did you think about the data? Getting up into these kind of pressures, getting up into Magnum velocities with a non-Magnum cartridge, for instance. feedback about the rifle, feedback about 7-SWC. Are you guys shooting 7-SWC? Would you consider it for a hunting rifle or for a long-range target rifle? Or are you currently running one? Drop those comments, and I'd love to join in on the discussion with us, and we definitely have more planned. We've got a couple more Sherman Wildcat builds coming up. We've got a 7 Sherman short and a 6.5 Sherman short, which I'm partial to. I hunted in Africa with the 6.5 SS. 5 shots, 5 kills. Absolutely amazing, performance potential. So anyhow, we'd love to know your feedback. Look for more Sherman Wildcats content. Look for more Alpha Brass content. All that coming soon. That concludes this video, and that means it's time to wrap it up. I hope you enjoyed this video. If you're watching Ultimate Reloader on TV and want to take advantage of free resources, exclusives, and hot deals, just hold your camera phone up to the QR code, tap on the link, fill out the information, boom, you're getting Ultimate Reloader emails. Don't forget to like and subscribe. Also, we're on Facebook, YouTube, Rumble, where we've got unrestricted content, and Instagram. Make sure to follow us on all those channels. Ultimate Reloader also has a commercial solutions division serving law enforcement, the military, and the gun industry. We have some unique capabilities, including a comprehensive suite of recoil testing and evaluation capabilities, trigger profiling, and more. Thanks again for watching.